Today on AI Paper Podcast, we are breaking down RISER, Orchestrating Latent Reasoning Skills for Adaptive Activation Steering from the team at Tongji University.
This one is really interesting. It's a fundamental shift in how we think about controlling these models.
It really is. And if you're an ML engineer trying to get more reasoning power without the crazy latency of chain of thought, you are going to want to pay close attention.
Definitely. They've essentially built a kind of digital prefrontal cortex for LLMs.
Okay, so here's the 1-minute summary for you. RISER goes way beyond static activation steering, where you just blindly inject one vector for everything.
Right. It's dynamic, a plug-and-play system.
It uses this tiny, super lightweight router to mix and match specific cognitive skills, like logic or math, completely on the fly during inference.
And this is the key part. It does this without ever touching the base model's weights. The results, the numbers speak for themselves. You're looking at accuracy gains of 3.4 to 6.5% on really tough benchmarks.
Yeah, things like MATH and GSM8K. But I think the killy feature is the efficiency.
Oh, absolutely.
RISER actually outperforms chain of thought on some tasks while being 2 to 3 times more token efficient. It's like it does the thinking in the latent space, so you don't pay for the model to write out its homework.
It's high-performance reasoning with low latency execution. A huge deal.
All right, let's really get into the weeds here. We talk a lot about reasoning and LLMs, but most of the time, we're just treating the model like a black box we shout at with prompts.
Right, and that's the recurring challenge, isn't it? We build these incredible, massive models, but they can be chaotic. They get lazy, they hallucinate, they use the wrong part of their brain for the job.
Like trying to write a poem with cold, hard logic.
Exactly. And historically, we've had, 2 ways to fix that? First, you've got fine-tuning.
The nuclear option.
Yeah, SFT, RLHF, whatever your flavor is. It's invasive, it's incredibly expensive, and you always risk catastrophic forgetting. You make the model a math genius, and suddenly it forgets how to code.
And then there's option 2, prompting. Specifically, let's think step by step, chain of thought.
Which works, don't get me wrong. But for anyone running this stuff in production, it's a nightmare. You're paying a compute tax for every single token of that thinking.
The latency, the cost, it just balloons.
Mm-hmm. And this paper, RISER, is really about a third way, activation steering.
So for the engineers listening who might be more used to things like RAG, how do you distinguish activation steering from, say, prompt engineering?
Okay, so think of it like this. Prompt engineering is like talking to a pilot. You're giving instructions from the tower. Fly carefully, check your instruments.
Okay.
Fine-tuning is like sending that pilot back to flight school for 6 months to retrain them. Activation steering is reaching into the cockpit mid-flight and physically adjusting the controls yourself.
You're directly modifying the internal activations, the residual stream, as the model is running?
Exactly. You inject a vector, just a list of numbers that represent some concept. You want the model to be more rigorous. You inject a rigor vector and physically push its internal state in that direction.
So we've seen this before with methods like CAA, contrastive activation addition. But the RISER paper makes a pretty strong case that those older methods have a fatal flaw.
They do. They're static. That is the whole problem.
What does that mean, static?
It means it's a set it and forget it approach. You extract a logical reasoning vector, and then you just add it to every single prompt that comes in with the exact same strength every single time.
So it's like locking your car's steering wheel 5 degrees to the right.
That is the perfect analogy. It's great if you happen to be making a right turn, but it's a total disaster if you're trying to drive down a straight highway.
Right. You ask the model for a creative poem, and it gets this huge, unwanted dose of logic.
And you get a very weird robotic poem.
Yeah.
So this is where the paper's biological inspiration comes in. The prefrontal cortex, the PFC.
The brain's executive controller.
Right. Doesn't do the math itself. It routes the traffic. It tells other parts of the brain what to do. If you see a math problem, the PFC fires up the regions for calculation. It's dynamic. So the authors asked, can we build a tiny digital PFC for an LLM?
And that is RISER, router-based intervention for steerable enhancement of reasoning. So it's a 2-phase thing. Phase 1 is building the library of skills.
Yep. You can't route signals if you don't have any destinations.
So how do they even find these cognitive primitives, as they call them?
They use a really clever version of that contrastive activation addition method. They take a huge data set of problems and feed them to the model with 2 different prompts, a positive one and a negative one.
Okay, so a positive prompt might be, think step by step, be rigorous.
Exactly. And the negative prompt is, answer immediately, use your intuition, just guess. Then they look at the model's internal brain activity for both, and they subtract the negative from the positive.
And what's left over should be the pure essence of thinking hard.
That's the idea. But here's the quality control step that a lot of other work missed. They use an LLM judge, Claude 3.5 Sonnet in this case, to score the actual answers.
Ah, so they're not just looking at the activations.
Right. They only keep the vectors, where the positive prompt got a great score, like over 80, and the negative one just completely failed, score below 20. They're filtering for the purest possible signal of what actually works.
That's smart. So once they have thousands of these high-quality vectors, what do?
They run PCA, principal component analysis, to see how they all group together.
And this is where it gets interesting. They found exactly 6 clusters. Why 6?
Well, it was an engineering trade-off, really.
Yeah.
6 components explained over 85% of the variance in the data. When they tried fewer, say 4 clusters, important skills got mushed together, like math and logic became one thing, which is too blunt.
And if they tried more, like 12?
It was just noise. You start getting redundant skills that don't really do anything unique.
Yeah.
So they settled on these 6 orthogonal primitives.
Let's list them, because this is basically the model's toolkit. There's numerical calculation, logical reasoning, ethical alignment.
Reading comprehension, scientific analysis, and domain knowledge.
And you said orthogonal, which is key here. It means they're disentangled, right?
Mm-hmm. The cosine similarity is less than 0.1. It means you can pull the math lever without accidentally pulling the ethics lever. They're like pure primary colors you can mix.
Okay, so we have our library of skills, the ingredients. Phase 2 is the chef, the router.
The router is the heart of RISER. It's a tiny little MLP, a multi-layer perceptron. We're talking like 5 million parameters.
Just to put that in perspective, on a 70 billion parameter model, 5 million is.
It's a rounding error. It's nothing. Less than 0.1% of the base model size. It adds basically 0 latency.
And this little router, it sits at a very specific place inside the LLM.
Yeah, in the middle layers, usually around layer 20 to 25 for a Llama or Quen model.
Why there? Why not at the beginning or the end?
Well, the paper argues that the middle layers are where reasoning really happens, where it crystallizes. The early layers are just, processing grammar. The late layers are just getting the answer ready. The abstract thinking happens in the middle.
So the router sits there, watches the hidden state of the last token go by, and then it has to make a decision.
And it outputs 2 things. First, a selection mask, which is just binary yes or no. Do we need math? Do we need logic? Second, and this is the really cool part, it outputs a strength vector, which they call alpha.
So not just what to turn on, but how much.
Exactly. Sometimes you need a gentle nudge. Other times you need a hard shove. The router then calculates this weighted sum of the skills it picked and injects that final composite vector right into the residual stream.
It's changing the model's mind in real time. Oh, I see a chemistry question. Let's dial up scientific analysis by 40% and numerical calculation by 20%.
That's precisely the idea. Dynamic composition of skills.
But how do you teach a 5 million parameter model to do something so strategic? The training seems really clever. It's a 2-step process.
It had to be. They started with what they call a supervised warm-up. And this is tricky because there's no data set for correct router decisions. So they had to make one.
They brute forced it.
Pretty much a grid search. For a big set of training questions, they just tried all the different combinations of vectors and strengths to see which ones actually flipped a wrong answer to a right one. They called those oracle labels.
So they found out what actually worked in practice and then trained the router just to copy those successful moves.
Right. That gets you decent baseline. But to get the really smart generalized behavior, they moved to step 2, reinforcement learning. They use something called GRPO, Group Relative Policy Optimization.
Why GRPO?
It tends to be a bit more stable for this kind of fine-grained control task. And the reward signal was super simple. Binary accuracy. Did the model get the right answer or not? Yes or no?
But there's a catch, right? There's this KL regularization term. What's that for?
Ah, yeah, that's the secret sauce. That's to keep the router from going crazy. An RL agent, if you let it, will find that cranking all the vectors to 100% might solve one problem, but it pushes the model's internal state so far off its normal path that it just starts spitting out garbage.
It basically lobotomizes the model.
Exactly. The KL term is a leash. It says, hey, go for accuracy, but don't stray too far from how the base model naturally thinks.
Yeah.
It keeps the whole system stable.
So it learns to steer, not to hijack.
That's a great way to put it. It learns subtlety.
Okay, so let's talk performance. Does this digital PFC actually work?
The numbers are really solid. On the math benchmark, which is brutal, RISER gave the model a 6.5% accuracy boost. On GSM8K, it was up 5.4%.
And this is all just at inference time. No retraining the big model.
Correct. But the comparison that I think everyone should be looking at is against chain of thought. CATI is kind of the gold standard for reasoning, right? RISER beats standard COFI on datasets like GPQA, which is graduate-level science questions. But here's the thing. It does it while using 2 to 3 times fewer tokens.
Because it doesn't have to show its work.
It doesn't have to show its work. The thinking is internal. With COFI, you're paying for all that filler text. Let's think step by step. First, I'll do X. That's latency. That's money. RISER gives you the benefit of that thinking process without the verbal baggage.
That's a massive efficiency unlock for any engineer working on production systems. You get the smarts of COFI with the speed of a simple prompt.
It really is. It suggests that reasoning isn't just a linguistic thing. It's a neural state. And if you can just induce that state directly, you don't need all the words wrapped around it.
I want to talk about interpretability, because usually these vectors are black boxes, but the paper has this heat map, figure 6, that's amazingly clear.
Oh, that's my favorite part of the whole paper. You can literally see the router's strategy. For the GSM8K math problems, you see the numerical calculation vector just light up bright red.
And for something like truthful QA,
that one goes dark, and ethical alignment just pops. It behaves exactly like you'd hope it would.
It gets even more interesting on the really complex problems.
Oh, yeah. On GPQA, it's not just one liver. It's this beautiful, complex mix. You see reading comprehension, science, and logic all firing and fading in this intricate dance as the model processes the question.
They had a great case study on this, the Max Weber question, the bureaucracy trap.
Yes. This is a classic test. Does the LLM understand, or is it just doing word association? The question is about Max Weber's theory of formally rational law.
And the multiple choice options include bureaucracy and capitalism.
And the base model, even with chain of thought, picks bureaucracy. Why? Because in its training data, Max Weber and bureaucracy are probably mentioned in the same sentence millions of times. It's a cheap statistical trick.
But it's the wrong answer in this context.
It's the wrong answer. And when RISER is active, you can see on the heat map the logical reasoning and domain knowledge vectors just spike. It actively suppresses that lazy, obvious association and correctly picks capitalism.
It stops the model from going on autopilot.
That's the PFC function right there. Inhibiting the impulsive, easy answer to find the harder, correct one.
Okay, but we have to be critical. No method is a silver bullet. What are the limitations here?
The biggest one is probably transferability. They found you can take a trained router from a big model, say 32 billion parameters, and put it on a small model, like a 7 billion one, if they're in the same family.
Like an inference time distillation?
Exactly. They put a Qwen 32B router on a Qwen 7B model, and the little model got about 5% smarter. So the geometry of thought, you could say, is similar across scales in one family.
But you can't take that Qwen router and plug it into Llama.
Complete failure. It's like trying to run PlayStation code on an Xbox. The internal brain structures are just too different. The vector for logic in Qwen might mean cheese in Llama. It's gibberish.
So you have to train a new router for each model family.
You do. And the other big thing to remember is you're only awakening latent skills. You can't teach new facts. If the base model has never ever heard of a specific concept, steering isn't going to magically invent that knowledge.
You can steer a car, but you can't make it fly if it was never built with wings.
That's a good way to put it. And, the fact that they settled on 6 clusters is a simplification. Real cognition is probably more granular. But for an engineering solution, 6 was the stable choice.
So zooming out, what do you think RISER tells us about where AI architecture is heading?
I think it's a huge signal that we're moving towards a more modular AI.
Mm-hmm.
For a long time, the goal was just build one giant monolithic brain.
Mm.
But now we're seeing the power of externalizing the control systems.
Separating the engine from the steering wheel.
Yes. Instead of just making the brain bigger, we're building better controllers to pilot it. It's a shift from prompt engineering, which can feel a bit like voodoo sometimes.
A bit, yeah.
To activation engineering,
Yeah.
which is precise, mathematical, and something you can actually reproduce reliably.
And for the engineers listening, this isn't just a theory. The authors have released the code for RISER.
They have, yeah. It's a very practical framework. If you're building agents or ARAG pipelines where reliability and cost are make or break, experimenting with this kind of dynamic steering could be a huge win.
It's a move away from just asking the model to please be smart And more towards installing a system that ensures it is.
A system that the model learns to operate itself. That's the real breakthrough.
A fascinating look under the hood of these models. That does it for our breakdown on AI paper podcasts. Thanks for exploring the latent space with us.
Thanks for having me. Keep steering.
We'll see you on the next one.